Section 7.2, graphing rational functions. Our objective for this lesson is to graph simple rational functions, translate those simple rational functions, and graph other rational functions. So first of all, we've been talking about this rational function idea. What is a rational function? A rational function is a function, let's go f of x, of the form p of x over q of x, where p and q are both polynomial functions. Polynomial functions. Okay. Basically, where we have a function divided by another function. Okay. The simplest of our polynomial functions is actually our inverse variation function from the last lesson. Our inverse variation is the simplest of our rational functions. Again, if you remember, our inverse variation was y equals k over x. And the simplest of these is when k is 1. So let k be 1. So then my function actually looks like the function f of x equals just 1 over x. That is my parent function for these simple rational functions. It is the simplest of my rational functions. So let's go ahead and let's create a table of values for this to try to get an idea on what its graph looks like. So let's put some x's and some f of x's into this. Okay, let's start with the simple. Let's put in a 1. 1 divided by 1 is 1. When we put in a 2, 1 divided by 2 is a half. When we put in a 3, 1 divided by 3 is 1/3. When we put in a 0, 1 divided by 0, if you remember for our maintaining mathematical practice, that's undefined. Okay. Let's put in a negative 1. 1 divided by negative 1 is negative 1. Let's put in a fraction. Let's put in negative a half. 1 divided by negative 1/2 is the same as 1 times a negative 2. Remember, multiply by the reciprocal, that'd be negative 2. So let's graph these points and see what we get. We get the point 1, 1, 2, 1/2, 3, 1/3, 0 is undefined, negative 1, we get negative 1, negative 1/2, we get negative 2. If we keep filling in points, what we end up getting is a curve, one that looks like this, and then the exact same curve over here. Okay. This shape is what we call a hyperbola. Hyperbola, kind of like a parabola, but it's a hyperbola. Okay, we call it a hyperbola. A hyperbola has two symmetrical branches. We call these both parts branches. A hyperbola has two branches. And the two branches are symmetrical, meaning that they'll lay on top of each other if we lay one over the other. Hey, it has two branches. Here we have one up here in quadrant 1, and in quadrant, this one's in quadrant 1, this is in quadrant 3. If you remember our quadrants, but they won't always be in those quadrants, but they'll always be in opposite quadrants, even 1 and 3, or they'll be in 2 and 4. Okay, there won't be one on top of the other. That's not how hyperbolas work. So we can either have 1 and 3 or 2 and 4. Okay, so they're in two branches here, and these have things called an asymptote. We've talked about an asymptote before. If you notice, this graph will get really, really, really close to the x-axis, but never ever cross it. Sorry, the y-axis. And this down here will get really, really close to the y-axis and never cross it. So there's actually an imaginary line, an invisible line that comes through there that this thing never ever crosses. We call that an asymptote. This one is a vertical asymptote. The parent function has a vertical asymptote, and the equation of this line, this orange line here, crosses the x-axis at 0, so the equation is x equals 0. But it also has another asymptote. It has a horizontal one, because it never ever crosses this line right here. Okay, so it never ever crosses that line right there. So it also has a horizontal one. And this is the equation of that line is y equals 0. That's the equation of that line. The equation of the x-axis is y equals 0 because it crosses the y-axis at 0. So our normal simple parent function of 1 over x graphs a hyperbola with a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. Let's talk domain and range. Well, we can see here from even me typing in my table here, I couldn't put a 0 in it. It never worked. So I can't put a 0 into this function, but I also can't get a 0 out. So the domain and range are really just all the non-zeros, so non-zero numbers. So they're non-zero. So we could say all real numbers except 0. Okay. Same with the range. The range is all real numbers except 0. Again, this is for the simple parent function. If I go sliding this thing left, right, up, and down, those domain and ranges are going to change. And we'll look at that here in a minute. Okay. So let's go ahead and let's graph another type of rational function here. G of x equals 4 over x. So let's graph this and let's compare it then to this graph. So let's go ahead and let's graph this. Let's do a same table of values. And let's put in similar numbers. Let's put in a 1 because we put in a 1 up before here, so let's put in a 1 down here. 4 divided by 1 is 4. So I put in a 1, I now get a 4. Now let's put in a 2. When I put in a 2, I get 4 divided by 2, which is 2. Here I got a half. Okay. Let's put in a 3. 4 divided by 3, well that's 4/3. Put in a 0. Again, that's undefined. Let's put in a -1. 4 divided by -1 is -4. Let's put in a -1/2. 4 divided by -1/2 is, let's see, 4 divided by -1/2 gives me 4 divided by -1/2. That's the same as 4 times a -2, -8. Okay. Let's graph these points and see what we get. The point 1, 4. You can already tell it stretches this point up. Instead of 1, 1, I've got 1, 4. Okay, and let's go 2. So 2, 2. Again, it stretched this one up. So I was at 2.5. Okay, so is that 4 times bigger? If I take a half times 4, do I get 2? Yep, 4 times bigger. Okay, 3. Before I had 3 1/3, now I have 3 4/3, which is 1 1/3. Again, it stretches it up. Again, 0 is undefined. -1, -1, 2, 3, 4. And then -1/2, -8, way down there. So I end up getting a new hyperbola if I keep plotting points. Okay, and I would probably want to plot a few more points over here. We can get a general idea on what this graph looks like. Okay. Okay, so here is my hyperbola. And if you notice from my original graph here, what did it do? If you notice here how close these points were to the origin, 0, 0, what happened here? It separated them from the origin, or it shifted everything up by a factor of 4, how we would expect it to. So it moved it, compare it with the graph of the original function, what did it moved it away from the origin. And if we think back to our translations, this is the same as taking 4 times 1 over x. So what's this 4 out here going to do? That's going to give me a vertical stretch by 4. So let's go back and let's look at how a rational function here is shifted. So we're going to go ahead and look at Desmos for a minute. So here's our general rational function, y equals 1 over x. Again here, because if you notice here I have sliders, my a is my 1, and here I have my h is 0 and my k is 0. Okay, so this is just the function y equals 1 over x. Okay, it has our normal vertical asymptote at x equals 0, or horizontal asymptote at x equals 0. But let's go ahead and let's change some of these h's and k's and see what it does to the graph. Okay, first let's mess with a first. So this is multiplying it by a factor here. First I'm going to make that a, instead of 1, let's make it a -1 and see what happens. So if I make it a -1, if you notice, that flips it over the x-axis. What was once over here is now over here. So it flips it over the x-axis, or it does a reflection in the x-axis. And that's what we would expect of that a out front. Okay, now let's look at making the a larger. Okay, so let's make the a larger. Let's go ahead and let's make it bigger here. And notice what's happening to the graph. Okay, as we make it larger, again, this is doing a vertical stretch. So this is stretching it up. So it's taking these points and stretching them up. So as opposed to 1, okay, when it's 1, here we have the point we can trace on this graph. Let me get it back. I could just type in. Okay, here we get the graph here. So when I make it a 2, it's just going to stretch my points up. Okay, so it kind of just stretches, keeps stretching my points up and up and up. Okay, so it does that vertical stretch. Okay, now let's look at this h equals 0, and let's see what that does. Let's make it 1, and notice what it does to the graph. It looks like it shifts it to the right 1, and that's what we would expect by adding or subtracting 1 inside. It gives me that horizontal shift. It's shifting the graph, but by shifting the graph, it also shifts the asymptote. Now my vertical asymptote here is not at 0, it's over here at that 1. And again, if you notice here, it's an x minus h. That's just showing us that it works backwards. When you're subtracting, it moves it to the right. When you're adding, it moves it to the left. But it shifts the graph over, but it also shifts that asymptote over. Okay, so the asymptote is not always at 0, at x equals 0. It could shift it over depending on that shift here. Okay, so let's make it back to 0. Okay, and then this k, if we think back to how our translations work, this is adding a k onto the end. So we would expect that to shift it up and down, which is exactly what it does. It shifts it up and down, which also shifts that asymptote up and down. Okay, so the asymptote here, if we were to put a 2 in, my asymptote is no longer at 0, it is up here at 2. Okay, so let's go ahead and let's add that into our notes. Okay, let's go ahead and let's paraphrase what we noticed in Desmos. In Desmos, we use the function f of x equals a over x minus h plus k. Again, this a is very similar to multiplying by this 4 out here. This 4 is out front. So we could write the a out front and have 1 over x minus h plus k, but we like to simplify it up a bit because I can write it together. But again, what does this a do? This a is my vertical stretch or shrink. Okay, just like in our old translations, it was our vertical stretch and shrink. And our reflections work the same as before. If I put a negative out in front of the function, what's it do? That reflects it over the x-axis. And when I put a negative inside the function, that reflects it over the y-axis. Okay, we didn't look at this one on Desmos because we very rarely reflect over the y-axis in a rational function, but it will act how you think it would. It will reflect it down instead of reflect over, which looks very, very similar, actually the exact same. Okay, and this minus h, again, is inside the function, so that's going to be our horizontal translation, is that minus h. So again, that's a horizontal translation, and again, it works backwards from how we think it would. So that also affects the asymptote. That affects that vertical asymptote. Because if I take this function here and I shift it to the right, the vertical asymptote is also shifted to the right. So you have to take that into consideration when writing your asymptote. Okay? That affects your horizontal translation, left, right. Yeah, sorry, I was right. That does affect your vertical. Got myself backwards. That affects your vertical. Okay, whereas a vertical translation, that's your K. Your K here, that's going to shift up and down. Okay, but as I shift up and down, that's going to affect here this horizontal asymptote. So as I shift up and down, my horizontal asymptote is going to move up and down. So that affects your horizontal asymptote. So when it comes to graphing these rational functions, I would first jot down how does it shift, and then from there graph your asymptotes first. So when graphing, there's a little hint, graph your asymptotes first. And I always do them as dotted lines, normally in a different color. Okay, and I'll show you in the next example. Okay, turn the page, example 2. So we're graphing a translation of a rational function. So first things first is I'm going to look at my asymptotes and see how it translates. Okay, so we want to graph this function. Well, this plus 2 here, that's inside the function, so that's going to shift me to the left 2. Okay, this negative 1 right here is going to shift me down 1. This negative 4 is going to reflect, and it's kind of out in front, so that's going to reflect over the x-axis. And this 4 is going to do a vertical stretch. So first things first, I'm going to graph the asymptotes first. So our normal horizontal asymptote, the normal horizontal line, is right over here, 0. But I'm shifting this guy down 1, so guess what my horizontal has to do? It has to go down 1. So my horizontal is going to be right here. So there's my horizontal. And now I'm going to write the equation of that line. The equation of this line, what axis does it cross? It crosses the y-axis. Where does it cross it? At -1. So this is the line y equals -1. So that's one of my asymptotes, y equals -1. So that's the vertical. This is going to shift it left 2. So let's take my normal asymptotes here at 0. We're going to shift it left 2. Okay, so it shifts it to the left 2. So here's my other asymptote. Okay, and this asymptote crosses the x-axis at -2, so this is x equals -2. So there's my two asymptotes, y equals -1, x equals -2. Okay, so now I've got my two asymptotes. Now, you just need to plot points on either sides of the asymptotes. So I'm going to go ahead and I'm going to create a table of values. And I'm going to use my calculator to help me out on these table of values. I'm just going to use it in my home screen. So I'd have -4. Be careful here. I want to divide it by this whole thing, so in parentheses. So let's try. What do we want to try in there? Do we want to try a 1? Well, we want to be on either side of my asymptote. My asymptote here is at -2. So maybe we should try -1. So we're going to go -1 plus 2, parentheses, because there's my denominator, and then subtract 1. And we get -5. The point -1, -5. So I can kind of tell where this is going to be. It's going to be over here now. So we tried -1. Again, you want to be on either side of your asymptote here. So let's go to 0. Let's put a 0 in. So when I put a 0 in this, I'm just going to second enter. I'm going to arrow back. We're going to change this -1 to a 0. We get -3. Okay, so we can kind of see what it looks like, and we can put a 1 in there also. So that's second enter, bring it back, let's put in a 1. We'd have -2.3, approximately. We put in a 1, -1, 2.3, so right about here. So we can kind of see it's going to come in and it's going to curve like that. And your asymptotes contain it, so you know it's going to be inside your asymptotes here. Now I just need to get some on the other side of my asymptote. So my asymptote's at -2, so let's put a -3. So again, let's put a -3 in there. Let's insert a negative, replace it with a 3. Oh, delete the 1. We get 3. -1, 2, 3. 1, 2, 3. Okay, let's put it at -4. See what happens. Then it's the 3, let's make the -4. We get 1. So we can kind of see it's going to do the same type of curve type scenario in here. You need at least 2 points on either side of your asymptote to get an idea on what the graph looks like. So there's my graph. So again, it shifted my original 1 to the left 2, down 1. It reflected it, if you notice it reflected, because it's not in quadrants, it's not over here in this square and this square, it's in these two. Okay? And then again, it shifted it, it pulled it out from where these intersect. That's that vertical stretch part. State the domain and range. Okay, the domain. Okay, so what can I put in for my x's? Again, your domain is your x's. What can I put in? Well, my domain, if we look at my x's, this is my x-axis. Okay, so on my x-axis, what number can I not have on my x-axis? What looks like here at -2. My asymptote, x equals -2. So my domain is all real numbers except -2. And where'd that come from? That came from that vertical asymptote. So then my range, so these are my x's are all real except -2. So then my range, so this is my domain right there. So now let's do my range down here. My range is all real numbers except, well, if you notice here, my y equals -1 is the line we don't ever cross there. So it's going to be all except -1. And that came from where? That came from my horizontal asymptote, y equals -1. Okay, so our domain is all real numbers except -2. My range is all real numbers except -1. Okay. All right, one last example, and then you can do some extra practice. Okay, irrational functions aren't always in this form. They don't always look like this, a over x minus h plus k. Sometimes we have to get them there. Okay, if they don't look like that, one trick is to long divide. So here in example 3, we have 2x plus 1 all over x minus 3. It's not written like this one, so let's long divide it. So I'm going to long divide. Okay, so I'm taking 2x plus 1 and dividing it by the x minus 3. I don't need a placeholder because we're decreasing by 1 each time. Okay, so now let's review our long division skills. X times what is 2x? Well, that's times 2. So now I multiply. So that'd be 2x minus 6. Draw my line and then I change my signs. And then I add. 2x plus -2x is 0. 1 plus 6 is 7. So I end up getting 2 plus 7 over my divisor, x minus 3. Well, if you notice, this looks a lot like this up here except for the order. So we're just going to, since it's adding, I can flip-flop it. So it's 7 over x minus 3 plus 2. So this function and this function are the same thing. So now I can just do this same process on this one. Okay, so I can figure out how it shifts left and right, up and down, find my asymptotes, state the domain and range. So what I'd like you to do is I'd like you to finish here example 3, now that I got you started. Finish example 3, we'll start with this question in class tomorrow. Okay, so finish it, graph it, state its domain and range. Okay, again, walk through the process I did here in example 2. And then here there's some extra practice. Okay, what I'd like you to do is I'd like you to only do some of them. I'd like you to do extra practice number 1, number 3, and number 5. We'll save the evens for class if we need them. So just 1, 3, and 5. Come to class ready to discuss.